Hello, hello, hello. Excellent. Thank you so much for coming, everybody. Although I actually can't see any of you. All I can see is the backs of my retinas because of the amount of light that is shining directly in my eyes. So, thank you so much for coming. I hope you've all had an amazing day so far and an amazing conference. The thing that I am going to talk to you today about is this thing right here. It is a wearable live captioning display. And it's made up of a flexible LED that can be mounted inside a mask, which live captions what I'm saying as I'm saying it. But before we dive into the tech, let me introduce myself. My name is Joe Franchetti, and I am a developer advocate at Ably. We're an edge messaging platform that helps developers like yourself to build live and collaborative experiences. We have an ever-evolving suite of APIs and SDKs that give you the freedom and flexibility to build collaborative apps like chat apps or order delivery tracking or multiplayer experiences or things like this, where stuff is happening in real time. And I'm primarily a web developer, but I do occasionally dabble in IoT. I put LEDs in my wedding dress so that people at my wedding could tweet a color at my dress and would change the whole color of the dress. I made a Christmas jumper that changes what emoji it's showing based on what Christmas song is playing. And I have to admit to a personal desire for seeing more products like wearable captions on the market. And that reason is my mum. So this is her, this is Mama Franchetti. And she's a smiley, quick-witted, sociable woman. And she loves to have a good natter with her friends. But she's also been steadily losing her hearing over the last few years. And it's a very isolating experience for her, as I'm sure it is for many other people. She relies heavily on lip reading and people enunciating clearly. And you know what makes clear enunciation and lip reading completely impossible is mask wearing. And obviously we want people, especially vulnerable people, and as much as she would hate me to say it, older people to be wearing masks to stay safe these days. It makes it really difficult for her to interact with people on a day-to-day basis. She can't understand what people are saying to her in shops. She gets very self-conscious if she has to ask people to repeat themselves, and she misses out on jokes that her social group are making. So people have a tendency, I don't know if you've noticed it, when you ask someone to repeat themselves more than once, people have a tendency to become rude, and they'll just say, oh, you know what, never mind, it doesn't matter. So I have a couple of asks of you during this talk, and my first ask is, if somebody ever asks you to repeat yourself, just repeat yourself. It's really difficult for people who are hard of hearing to only be in on half the conversation. So please, be thoughtful, try and include people where you can. And as we've traversed her hearing loss, one thing has really struck me, and it's that we as developers, we're really not doing a very good job at making assistive and aging technology. My mum has a cochlear implant, which is a device that is implanted literally into her head, and it can stream sounds from her devices basically directly into her brain. And it has a little battery that clips over her ear, and it's super cool. Like, my mum has technology literally embedded in her head, like she's a cyborg. And there's quite a few problems with this device. The first thing is, it only runs, the app for this only runs on iOS, and she's always been an Android user, so she's had to entirely swap phones, learn a new operating system. And not only that, iOS released an update a year or so ago that for everybody who had this particular brand of cochlear implant, they heard screaming streamed directly into their ear for hours. They all had to take their cochlear implants off, turn them off. They were unable to hear. iOS basically turned off hundreds of people's hearing for a few hours, which is just really, it's not acceptable. We need to be better at testing. We need to be better at thinking about accessible technology when we're building. And I know assistive and aging technologies aren't very sexy, and they don't get the attention that the more glamorous tech gets. But we can really do better than this. And honestly, in 40, 50 years, that's going to be us that need the assistive technology. So, let's do our future selves a favor. So my second ask of the talk is this. Let's put some effort into assistive and aging technology. We are all brilliant humans, and I think that we can really make a difference. So story time and lecture is almost over, I promise. We will get to the tech. But I was really worried for my mum. She felt even more isolated than the rest of us did during lockdown. And assistive technologies that run on her phone, things that she already had, meant that she had to be looking down at her phone while she was talking to people. And people thought that she'd switched off from the conversation or that she wasn't listening to them, and they'd go and talk to somebody else. So I wanted to build something that I could wear rather than that she had to wear, that would mean that she could look directly at my face when I was speaking to her, and we'd be able to hold a conversation. And I'm a developer. We all love to fix problems. I thought this has to be something that I can build. And inspiration struck me in the strangest of places. So if you've ever been to London, or if you're coming to NDC London next year, I highly recommend you check this place out. It's called Cyberdog, and it basically sells rave clothing. So stuff with a lot of lights on it that you can wear to parties. And they were selling this thing here, which I have one of here, which is a mask which has LEDs in it. And it has a reasonably high resolution display that can do all kinds of fun animations. And I bought one immediately thinking, this is perfect, this is exactly what I need. I can display text on that and I'll be able to wear it so my mum can look at my face when we're speaking to each other. However, it wasn't quite that easy. The display that comes in the mask has little tiny chips built into it, which you very much cannot write to. I couldn't backwards, it came with a very dodgy app, which was written in Chinese and completely obfuscated, because it was clearly full of spyware and all sorts of awfulness. Couldn't reverse engineer it, couldn't work out how it was working, tried to sniff the Bluetooth packets that were being sent, and I just really couldn't reverse engineer this thing. So, not wanting to be beaten, I thought, I can make that myself. How hard can it be? So, let's do that now. If we break down the mask into its component parts, what we really need is we need a flexible LED array of some kind, which will contain something called addressable LEDs. And addressable just means that we can send data to each LED individually to tell it what color to turn, how bright to turn, how long to turn on for. Then we need a way to control that display, so we're going to need some sort of microprocessor board, and we're going to need a small battery, something, about this size, that can power the board. And it all needs to be able to fit inside a mask, really. And the final thing that we will need is a microphone and some sort of speech recognition software. And the addressable LED display looks a little bit like this. So I've got a larger version here, which you might be able to see. It's nice and flexible. It has these very small LEDs on it that have their own little tiny processors. And we can put small holes in it so that you can breathe through it. And it's powered by a very small microprocessor. I don't know if you can see the size of that, but it's teeny tiny. And the brilliant thing is, it's small enough to fit inside a mask or inside your pocket. It can be powered by a USB battery, and it has Wi-Fi on it. So we can hopefully easily send data between the mask and other devices. And I could put a tiny little microphone on the board and have that inside the mask listening to me. But we all carry microphones around in our pockets with us every day, attached to our phones. And as I mentioned before, the board has Wi-Fi, so I can communicate between my phone and the board by using a web app, for example. There's the microphone. So if I made a web app, I can use web APIs, which make it really easy to use the phone's microphone. We grant permissions, it listens to what I'm saying, and then it's going to use a service to translate the speech that is picked up and return it to the phone in text form. And I used Azure Cognitive Services for this. If you've not used Azure Cognitive Services before, I'm sure at NDC many people are familiar with them already. It's a suite of APIs that allow you to add AI capabilities to your apps. And one of those capabilities is speech to text. So the web app is just a simple Node app that uses a few different packages. So we're using the Azure Cognitive Services Speech SDK. We're using a driver for the LED display that I actually wrote for a different project, and I will talk about that later. And we need some sort of transport protocol so that we can send data from the phone to the mask. The app itself has some really basic UI. It looks like this. We have a button, which when you press, you can get permission to use the microphone and start streaming audio. Then we have a text box, which actually shows the returned text that comes back from Azure Cognitive Services. And along with that, we have this visual representation of the LEDs in the array, which are just divs on the page. And then we also have some settings, so I can change the color of the text, and I can change the speed that the text is scrolling at. So let's start by hooking up the Start Listening button and sending data to Azure Cognitive Services. So here, what I've done is I've wrapped the Cognitive Services Speech SDK with this code here. And under the hood, Azure Cognitive Services is using Get User Media to listen to the microphone. Get User Media has been in the browser for ages. It allows us to prompt the user to get permissions for their microphone and their camera. In this case, we only need the mic, so that's great. The fewer permissions we ask for, the better. And then we get a stream of their data from their media devices. So when the user clicks on the Start Listening button that we saw on the UI earlier, a function called Stream Speech from Browser is called. And this uses the Azure from default microphone input along with an authorization token, which will allow us to authenticate with Azure, and it will initialize a speech recognizer. And this speech recognizer is what is going to actually perform the speech recognition on the data which is coming from the mic. And it returns an object which contains the text of what has been said. It's great. It's a really nice, easy-to-use API. And in the main app, I wrap the Azure Cognitive Services with a class, which allows me to provide it with an API key, and then we register on text recognized. And this callback subsequently calls the Matrix LED driver, which I will talk through in a bit. But first, let's talk about actually communicating with the hardware itself. So how do we get this transcription, which we now have on the phone, to the mask? We need some sort of messaging protocol. And the one that is usually used for IoT is called MQTT, the Message Queuing Telemetry Transport. And it's a lightweight publish and subscribe protocol specifically designed for IoT devices. It's optimized for high latency and unreliable networks. And it's perfect for this kind of project where the wearer might be on a dodgy 3G connection. In order to use MQTT, we need some kind of broker, and this is a service which is responsible for dispatching the messages between the sender and the rightful recipients. The web app, in this case, is the client, and the recipient is the microcontroller that is attached to the LED display. And I'm using the Ably MQTT broker for this. This is great because I can use the Ably JavaScript SDK in my web app, and Ably will automatically send all the messages out over MQTT as well as over WebSockets. So I can not only connect the IoT devices to it, but I can also connect other phones to it. So if my mask happens to break, or if I'm speaking to a lot of people who would like to see the live captions, they absolutely can on their own phones. As I mentioned before, the microprocessor is really small, and therefore it has very limited memory, limited power, limited processing power, which means that we need to optimize the code that runs on it as much as possible and be as efficient as possible. We want to avoid doing things like text parsing, which is actually quite complicated and memory intensive. Parsing and splitting strings is especially costly, and it involves quite a large buffer. We don't want to be using up all of the memory on the board processing the text. So to solve this problem, I created a binary message format which talks to the hardware. The browser app creates a specifically encoded message to send the text strings to the device. So let's have a look at those. So most of the time, when we're sending data, we're used to sending JSON. We might want to send something that looks like this. But instead, we're going to use this binary format to encode this data in a much more packed down format. So for example, we might have a message like this, where we want to be able to tell the browser that we are scrolling we want to be able to tell the device that we are scrolling text. We want to be able to tell it what the text is, so in this case, my line of text. And we want to be able to tell it how fast to scroll it and what color to scroll it in. So we're going to try packing it down into a binary message to make it as small as possible. And the way that we do that is packing it down as raw bytes and using control codes from the ASCII standard to provide header information about the messages. And because the message is a raw byte stream, we then don't need to actually pass it on the hardware. We can just loop over each individual byte and run a different process depending on what the byte says. And this takes all of the complexity of parsing text away from the microprocessor and moves it into the JavaScript code, which is running on the phone instead, which is much easier to debug, much easier to test, and just the phone has a much higher processing power than the tiny little microprocessor does. So if you have a look at this table here, the byte at offset 8 could represent a single text character. But the parser on the hardware is looking for the start text and the end text markers. So these two here. And what this means is we can send any number of ASCII characters in between STX and ETX to form full sentences to send in the message. So that is how we can send messages. We've now packed them down into this binary format. Let's look at actually hooking up the speech recognition. So earlier on, we registered a callback to onTextRecognized that called the matrix LED driver. What we didn't look at is how we create a connection between the browser and the LED driver using Ably's MQTT broker. And there's a few things going on in this code sample. So first of all, we make an instance of the Ably SDK. Next, we new up an instance of the remote matrix LED driver, which is part of the display driver package. And it takes a display config, which changes how we encode the pixel data. So it needs information about what size of display we are showing on. And it also needs a device adapter, which is the implementation of that encoding protocol that I just described. The Arduino device adapter that you see here implements that cool binary encoding protocol that we talked about. And it requires a transport, which in this case is a wrapper for the Ably JavaScript SDK, which is how data is being sent out. When the data is sent out over WebSockets by the Ably JavaScript SDK, we get the Ably MQTT data for free as well. So this is a lot of information, and I'm sorry to sort of just dump all my code on you all. But what we have here means that when we call the functions available to the matrix driver, it knows how to convert pixel locations to absolute numbers on the display. It understands how to encode those numbers in a wire format, and it knows how to transmit the data over MQTT. So if we were to visualize the entire process, it looks like this. So now we have a way to send nice compact messages. Let's take a look at the display driver itself and how it actually reads those messages. So the device driver was written for a previous project. I made a little t-shirt that had a square 16 by 16 array of pixels, and I made a little web app that was kind of like very small MS Paint, and you could color each of the pixels, and people could color in what was on my t-shirt. So the driver has a few different API calls. So one of the things it can do is it can set individual pixel colors, either in a hex or RGB format. It can also set single pixels. Imagine if we just had a single strip instead of an array. We can also set the entire display at once by using these nice visual coordinates. So each LED that is illuminated with a hash there will show up bright on the LED display. I can even send entire images to the LED display as long as those images match the number of pixels in the display. So if we have a 16 by 16 image, it has to have 16 by 16 pixels. But for the mask, the driver needed to be extended to include text and scrolling text, and also an optional color and a speed setting. So that's going to potentially look like this, and then like this with our color and speed setting. And as you'd imagine, scrolling text is a bit more complicated than setting individual pixels on a display. So let's take a look at how to do it. I'm going to take a drink of water. So the first thing to do was to design this pixel font right here. And what I've done is I've chosen a set of alphanumeric characters that I think I'm most likely to use in day-to-day speech. And I need to convert these into an array of binary values. So I took a guesstimate at what I think I would use: the letters of the alphabet, a couple of bits of, what else have we got there? Some symbols, some numbers, some punctuation. And what I'm going to do is convert this pixel font into an array of pixels. So let's start with the letter N, for example. Visually represented, the N looks like this. And if we give a value to each of the pixels that makes up the N, then the values would look like this. So we have zeros for any LEDs that are turned off, and 1 for any LEDs that are turned on. And if we then look at what that array actually looks like, it's like this. And if we put it all in a long line, it looks like this. So this is the letter N represented as an array of bytes. We've encoded it into a 4x8 block, basically. And instead of encoding the entire alphabet by hand, which would have taken absolutely ages, luckily there is a JavaScript image manipulation library which will actually do this for you. And it's called GIMP. There's a link to it right there. So I was able to convert the font sheet that I made into an array of individual pixels. So I've taken liberty with this for screen design, but if you imagine this whole font as one long line, you may have noticed that the characters aren't all the same width. I personally think it looks nicer. I find monospace fonts much more difficult to read. But what this means is that the array of bits that we just created will need a list of indices to say at what point each letter starts, so that we know where in the array that letter is. And we also need to know the width of each letter so that we know when that letter ends. But that's just another array of bytes, and honestly, they're both the encoded font and the array that says the indices and the width. This is a really small amount of information, and it's small enough to be embedded on the microprocessor, which is great. And this means that instead of computing all of the individual pixel positions in the browser app and sending them one by one, the microcontroller can actually just handle that translation itself, which saves us a lot of data when we're sending over MQTT. So cool, we have a font. Now we need to work out how to display it on the array. And as always, I don't know how many of you have worked with hardware projects before. It's never as simple as you would like it to be. So I learned that there are multiple different ways that LED displays can be wired up. So this one here, if you want to come and have a look at it at the end of the talk, feel free. you probably can't see, but on the back you can see how the wiring works, and it's going up and down like this, vertically up and down the display. But there's also a whole load of other options. So when we talk about arrays of addressable LEDs, what we're saying is each LED has its own number, it has its own address. The first LED on the strip is LED 0, and so on as we move through the array. And we need to know not only how many LEDs there are, but also how they're wired up. So some common wiring patterns that I've seen are like number 1 here, which is reading order, where we start at the left, we move to the right, the wires go back again, we start at the left, we move to the right. There's also these 2 other modes, 2 and 3, which I have named snake mode because the wires snake. So we have snaking horizontally and we have snaking vertically. Not only that, but I don't know, again, if you can see on the back of here, but these connectors can be connected at either end. So the data could be going in at the right-hand side, it could be going in at the left-hand side. So we need to make sure that we are accommodating these physical constraints so that any different kind of display can be used with our microprocessor. So I need to ensure that any operations in the JavaScript that refer to a pixel location understand that they're using a coordinate system rather than a pixel ID. But that's all very doable. We can calculate if we know the width and the height of the matrix, and we know what type of wiring mode it is, we can do that maths. So once the coordinates are sent to the hardware, it will then translate these coordinates into the correct pixel ID based on what configuration we've given it. So our configuration looks like this. I need to give a little bit of information to the board to tell it what display it's powering. So the microcontroller has this single configuration file, which allows me to set up things like the Wi-Fi name, the password, the MQTT settings, but also I need to tell it which pin on the microprocessor board the data is coming out of. That's the GPIO pin, a general purpose IO. Then I need to tell it the dimensions of the display. So in this case, it's 8 by 28. And then I need to tell it which kind of carriage return mode we've got. So which direction is it snaking, which end the data is being sent into, and also, and this one has caught me out on a project before, what type of LEDs we're using. So if you've ever worked with RGB LEDs, you may have discovered that there are 2 different types. There's RGB and there's RGBW. RGB takes 3 colors, very similar to how we're used to setting colors in CSS. RGBW takes an extra value, an extra 4th value, which is the whiteness, so how bright you want the color to be. If you send 3 values to a LED that's expecting 4 values, it's not going to display as you want it to on the mask. So just double check when you are working with LEDs which ones you've got, because I spent many hours debugging that one. So when the message arrives at our device, it runs through this initial parsing block and interprets what the message said, so what was sent by the LED driver. It checks the first byte for the control code and then the second byte for the control mode. So is it a pixel? Is it some text? Is it scrolling text? The Arduino device driver then needs to be updated to send messages using the correct control mode, so either text or scrolling text. So let's have a look at that. So we know already that we are able to set a display size, and we have the font array stored on the microprocessor already. The missing piece is to write some message handlers which are going to process the incoming binary messages, and these handlers are going to look up that font data and push the appropriate pixels to the display. So when we get a message that says, I've got some text, I want you to display some text, the code will loop through each character in the message and look up that character in our embedded font array. And it will then return the array of bytes that we saw earlier, prefixed by the width of each character. And because the font data includes the width, when the code iterates over subsequent characters, it can work out where it has to place them next. It can calculate the location that it needs to start drawing at. And if we call this location X position, so the position that we're going to start drawing at, each time a character is drawn on the display, we know the character's width, so we move the X position along by the width of the character and also by 1 pixel, so we have a nice gap in between each letter. And this continues until the loop reaches the width of the display, and then it stops drawing, because the extra characters are just going to flow off the end of they're not going to show on the display. So that's how we display text. But how do we scroll it then? So writing scrolling text is mostly the same with one subtle change. So if we think about how we calculated our X position, what we're going to do is start off with the X position on the right-hand side of the display. And when that message is first received, the X position is going to therefore be equal to the width of the display. So in this case, 28. We can then write a loop that will decrement that X position until the total number of characters has been run through the entire display. So if the text string has a total width of 100 pixels, it'll keep on drawing and decrementing that X position until the X position equals -100. And this will gently scroll the text across the screen, which is super awesome. You can see the code for that here. So if the message mode indicates that we've got scrolling text, we start a while loop, which will update the scrolling position in the byte array that represents the entire fonted string. It starts looping and displaying a subset of the total data to the string until all of the pixels are scrolled off the screen. And the nice thing about this is we can then really easily implement a scrolling speed by just changing the delay that happens in between each loop. And another cool thing about this is that because we've got this loop, we're preventing control being returned to the main Arduino code, which would then trigger receiving more MQTT messages. So we can actually use MQTT as a buffer for our messages rather than having to, for example, store them on the board. So once it finishes scrolling the last piece of text that it receives, it then goes back and checks whether any subsequent messages have been sent and starts scrolling the next piece of text. And that is it. That is how we build a live caption display. That's how I built a live caption display. And here's the finished result. This is me showing it to my incredibly bemused mother, who was really unsure that this was actually the solution that she needed. But, you know, I tried. And there is some more if you are still interested. There are a few parts of the app that I've not spoken about because otherwise we'd be here all day. One of which is, you know, obviously not everybody has a wearable LED mask with them, so no problem. The app itself also shows the return text as text, so we can go back to the situation where we're just reading from our phone if we need to. And this is just, it comes for free because we're using the Ably JavaScript SDK. Everything's being sent over WebSockets. So if you visit livecaption.ably.dev, you will be able to see what I'm saying as I'm saying it. Although, so saying, Azure Cognitive Services was having a 503 earlier today, which is, I think, why this keeps turning off and back on. So if anyone from the Azure team is here, can you tell me what's going on? But yes, in future, you will be able to visit livecaption.ably.dev for all of your captioning needs. Another of the things that I've not mentioned is the visual representation of the board in the app, and this is super cool. So behind this is a full Arduino emulator, which runs the exact same code that the Arduino itself is running, and outputs it to divs instead of to individual pixels. The reason why I built this is because, again, if any of you have ever worked with hardware, it's such a slow debug cycle. You know, it takes sometimes 3 minutes to push the code to the board. You then have to, you know, plug in your serial monitor and double check what's happening, and it's just slow and frustrating. So I built this visual emulator so that I could debug in the browser without having to have all of this plugged in on my desk. The good news is that all of this code for this project is on GitHub. You can absolutely take it and make it your own. It is all open source. If you would like to see any of it, you can find it at github.com/ablylabs/live caption demo. And there's a whole load of other projects there in Ably Labs as well. So if you want to build a chat app, if you've got other IoT projects, if you want to build multiplayer games and quizzes, there's a whole load of free open source demos for you there. Please check them out. Please make them your own. And if you do decide to build something with this project, if you want to build your own LED devices or Christmas jumper or wedding dress or anything, let me know. I really would love to work with you on it. Tell me about what you're making. I like making sparkly things, so I'm really happy to do that with you. You can get me on Twitter. I am at @thisisjoefrank, or you can join the Ably Discord, where you can chat with me in real time. I'm always happy to talk about any real-time projects, so do give me a shout. If you've enjoyed this talk, please give a tweet to @Ably Realtime so that my boss knows that I'm hard at work today. And I also have some cute little stickers down here, so if you would like some stickers, please come and grab some. Thank you all for listening. If you have any questions, I don't know if we have a mic or if you just want to come and talk to me at the end, feel free. If you want to come and have a play with any of the bits of hardware, also come have a look. But yes, thank you so much for listening.